Okay, so in this video I'm going to talk a little bit about the top-down design approach and how it was used in designing the current car that we have in the CAD model. So one of the first things we set out to do was define the specifications and parameters and the important numbers that we wanted for this vehicle. And the way we did this was doing a lot of research on what other top 10 and top 3 schools were doing, kind of taking an average of what they were running for their track width, their ride height, their wheelbase, and a few other things like suspension design. We wanted a smaller car, obviously, so we chose a wheelbase of 49 inches, which is significantly smaller than the car from the previous year. And then we also wanted to make the front track width wider than the rear track width, and that was to promote oversteer, or breaking the rear end of the car loose, because a lot of the top teams are doing that. So taking averages of some of the top teams, we came up with 52 inches for the front track width and 48 inches for the rear track width. And there's some of them that are even more extreme than this, with almost a foot difference between the front and the rear track width, but we figured these were pretty safe numbers to stick with. Another important thing to decide on pretty early on is the ride height and the droop for your suspension. These are all numbers that are going to drive your top-down design approach and allow you to make skeleton geometry, skeleton parts that will allow you to finally create the final models. So starting out with the front track width and the rear track width and the wheelbase, this gives us a good starting point to put some geometry into the CAD model. So I'm going to go over to NX. I've got the car pulled up right now. First of all, this is everything in the model that you'll see. This is datum coordinate systems, datum planes, datum axes, and all the solid bodies and assembly constraints. If I want to just look at the solid bodies, I can use the shortcut Control W. That brings up the show and hide box. The first thing you'll do is go to the very top and hide all, and then you're going to come over to bodies and click show. So now I've got the model up, and if I want to rotate that around, I'm going to click down on the middle mouse button on the scroll wheel and move the mouse. So I can rotate all around. And if I want to pan, I'm going to click the middle mouse button and the right button and then drag the mouse around. And then zoom, that's just the middle mouse wheel back and forth. Anyone who's familiar with NX will recognize this. So what I was going to explain, I'm going to go ahead and show everything again. Now over here on the right side, you'll see the assembly navigator, and this contains the base part and all of the sub-assemblies contained within it. So in the top-down design approach, you start out with a base part, which is 000C.8 currently in our case, and from there you assemble everything else within it. So this base part represents the topmost constraints on the system. So in this case, I'll show exactly what's in that part. I'm going to go and highlight all of these right here, right click on them, and show and hide. And I've also got a few assembly constraints. I'm going to hide those. So right now I'm in the top level part, the 000 part, and this is all there is to it. there's the datum coordinate system, the one that is the absolute reference geometry for 0, 0, 0, and then there's two other datum coordinate systems, and these are the front wheelbase and the rear wheelbase. This is the center of those. So from our other constraints that we looked at earlier, the wheelbase was 49 inches, and I think that may have changed from when we laid out these numbers, but the bottom line is the distance between this datum coordinate system and this one, that's what's going to be your overall wheelbase. So in this case it's 53 inches. We ended up making this a little bit longer because driver comfort and a few other things. The suspension geometries required a little bit longer wheelbase. And then another important decision that had to be made, this was after actually measuring it with a person in there, was the distance from the bottom of the roll hoop to the front wheelbase, which is now 35 inches, and then the bottom of the roll hoop to the rear wheelbase. So these datum coordinate systems are the only thing that's contained within the 0, 0, 0 top level part, and on these coordinate systems everything else will be assembled. So early in the design it was decided that the front suspension, the rear suspension, and the driveline and the ergonomic systems would be created separately as their own subassembly, and these would all assume that their reference coordinate system was either this one, or this one, and build off of there. That way, when you assemble one of the subassemblies into the main part, all you've got to do is constrain it to exactly match one of these, and it fits right in place. No matter what you change on your subassembly within that part, it's always going to just be matched up to this coordinate system. So, for example, the front suspension, that was one of the first parts to be taken on, the first subassemblies. You can see that I didn't mention the front suspension is 003, and you can find that on the part numbers spreadsheet on the Google Drive. You can see that in the 003 front suspension subassembly, everything associated with front suspension is assembled into this part, and its parent is 003. It's got no relation to anything else, any other parts, or 000 C.8. So I'm going to show just the front suspension. This is the front suspension subassembly, and I'm going to hide a few things, the datum planes, assembly constraints, datum axes. Now, it looks kind of messy, but you can see right here this highlighted coordinate system. That's the only reference to the original part that's used to assemble the front suspension into the part model. And the same thing for the rear suspension. Those are all the parts that are assembled in the rear suspension. If I want to show that, right here we've got both suspensions. They're created independently of each other, but because we use the top-down design approach and the original constraints, when you assemble them in the main model, they line up exactly where they need to be. You can see the rear wheelbase center right here. The rear suspension is just matched up to that and nothing else. And the driveline subassembly, same way. This is the chassis and a few ergonomic components. This is more ergonomic stuff and body panels and the firewall. And then finally, brake components. So you can see that once all these things are shown at the same time, they fit together exactly where they need to, but they're not dependent on each other, which is the right way to model it. That way each subgroup can modify things and without screwing up the other subgroups. In another video, I'll talk about the top-down design approach for the chassis by itself, because that was a little bit different than what I just explained here. But those are the basics of how the Baja car can be assembled in a CAD model and use a top-down design approach to drive your whole design. I will mention one more thing. I'm going to actually go in and just look at the front suspension, because this is a really good example of taking the top-down design approach and using the base numbers to create something that actually works and is functional. So I'm just focusing on the front suspension right now. I'm going to hide everything else except for the very first sketch. Okay. So there's a lot of datum planes in here, but those are here for a good reason. So we start off, everything right here is in the 004 part, and we call this the skeleton or the base geometry for the front suspension. So the 003 part, in kind of the same way that the 000 part is the base part for the entire assembly, 003 is the base part for the front suspension, and within it all of the subcomponents of the front suspension are assembled. So if I were to hide this one, this is, aside from those few lines which shouldn't be there, this is all there is to it for the 003 part. It's just datum coordinate system. So we'll take a closer look at the 004 part and show how the front suspension originated. So I've just made this the active part by double clicking on it. You can see that everything else is grayed out, a little bit more transparent, and this one is highlighted. Now if I go over here to the part navigator, I can see everything that's been done in that part. I'm going to start out from the top. This is the coordinate system for the 004 part, and I've got a few things that aren't showing right now because they were hidden earlier. So I'm going to go ahead and show everything in this part. So the very first thing we started out with was an axis, and you can see that here. This is just the axis along the coordinate system, something we can start out with, and then there's also a datum plane right here, which is labeled ride height. Now that's based on our original number. That's 12 inches down below the coordinate system right here, which is intended to be the bottom of the chassis. So we're starting to create some geometry here to try to figure out a model for this entire system. The next one is just a sketch down here, and that sketch, you can tell that it's dependent on the ride height plane, because you see that ride height, that plane turns red when you click on this sketch. And what this sketch was intended to be was the front track width. So just a line down there, and it should be 52 inches wide, and it's at ride height. So this is just used as a reference. The next one is the rake angle, and for the rake angle, that was another thing. If we look at the presentation, we decided on 8 degrees. So this rake angle plane is just inclined 8 degrees from the ride height plane, and it's using this line here as an intersection. Now, if we look at the next item, that's the wheel travel plane. So that's perpendicular to the rake angle plane. That's how this plane is defined, and you rotate it about the same axis. So we're starting to define even more geometry, because you know that assuming that the front suspension is a double wishbone setup, and those are going to be parallel to the rake angle plane, then it's going to have to move in a perpendicular fashion to that plane. So that's why we call this the wheel travel plane. And it's actually on this plane that the sketch is made for the skeleton geometry. So this is a 2D sketch to try to sort out some of your suspension parameters and figure it all out in 2D, get everything working right before you move on to 3D. So I'm going to double click on that sketch and go into it. This is all dimension now, but it started out as just trial and error and a few ballpark measurements and a lot of iterations to get it down to something that actually worked. Some of the things you do know are presumably the wheel height. So we've got 22 inches here because we're going to use 22-inch tires. And then you've still got the 12-inch constraint for the ride height. So this sketch right here is going to represent the bottom of your chassis. And then you've got 3 different lines here. So this will represent the lower A-arm, this will represent the steering link, and this will represent the upper A-arm. Over here you've got a line to represent your knuckle, a line right here to represent your spindle or axle, and that connects perpendicularly to your wheel. This line right here represents your shock, and then this line right here represents a common point of attachment for all of those. So originally this line was intended to be the shock, but after a lot of different iterations, several points were added up here, and these eventually became where the shock actually mounted. So by starting out with these couple constraints, you can see things deviated a little bit at the very end from the initial plan, but it served as a really good starting point to get an idea. This right here was supposed to be our front track width line, and our ride height was right here. So just starting out with that, you can figure out you want to have a foot box approximately this narrow, and then your wheel and your spindle needs to be out here at this point. And you can start out designing at ride height, so you can set the bottom of this wheel to be on this line right here. And that's exactly what it is right now. And then from there, you can modify all of your different parameters. So if I just modify something right there, I can see how the entire suspension geometry changes. If I modify the spindle height, I can see that I get some camber change right there. And you can see if you've got everything properly constrained, you can kind of run it through the travel just by dragging the sketches around. And by doing this, you can check some of your different parameters, like your camber change throughout the range of travel, and you can figure out exactly how far you can move the suspension before you run out of shock travel, assuming you already know your shock mounting locations. So the 2D sketch is a really powerful tool to start out and get the base geometry for your suspension. It's especially helpful for the double wishbone setup on a front suspension. So I'm going to get out of this sketch and show you what's next in this 004 base geometry part. So this is the skeleton geometry sketch we were just looking at. The next thing we have is the suspension plane, which is going to be based on the wheel travel plane and the skeleton geometry. So I'll show you how that's actually defined. So we've got perpendicular to the wheel travel plane passing through this line right here. So this plane is just setting us up for the lower A-arm. This is going to be the plane where the lower A-arm will sit at ride height. We've got a datum axis right here, the left lower pivot, so this is going to be the axis on which the lower A-arm pivots. We've got the upper suspension plane. It's defined in pretty much exactly the same way. It's perpendicular to the wheel travel plane, and it passes through the line or the point defined by the connection of the upper A-arm. And then I've got a couple other planes that ended up getting thrown in there to modify a few things towards the end. But what I've just explained is a good way to start out and get your suspension geometry. The rest of these we're not going to really worry about now because they were just used to make minor changes later in the design. That's not really important right now for the top-down design approach. This was added in a little bit later. This is actually the connection for the steering link, the steering box. So, coming off of that, here is one of the first parts that was made off of the skeleton geometry, and this is basically a skeleton upper A-arm. You can see there was a lot of different A-arm geometries considered. They're just sketches right now. These didn't even end up being the final part, but they were still helpful in evaluating the geometry. So this right here represents the first step in taking your 2D geometry to 3D. I'm going to go into this part just to give a little bit of an idea about it. So we've got our datum coordinate system. The first sketch was just a simple triangle, and this part was made on its own but assembled into the model based on its positioning with these different planes in the skeleton geometry. So right now it's just these couple different sketches just to try out some different ideas. But that's how you would do it, and you could start out with just the triangle like this, and then you could assemble it into your front suspension part and then start modifying things in place. So you can see that it was made to go right to the very end of this front suspension part, the knuckle. That's just the base of geometry. And then when you take into consideration that you actually have to use a heim joint, some sort of rod end to connect the A-arm to this knuckle, you've got to back off and make the A-arm finish a little bit before where you anticipate it attaching to the knuckle. But this comes a little bit later when you've actually got hardware picked out. Now you can see that 3D things are starting to make their way into the model. This is the lower A-arm. I'm going to make that the work part. And again, it's the same sort of thing, just another part with a few 2D sketches in it. And you're using the geometry that you made to constrain this. So I'm making sure that my A-arm is going to fit within the constraints of attaching to the chassis right here, having that right here as the pivot point, and still being able to attach to the knuckle out here. So I'm just going to start showing all these. So you can see with a little more development, now there's a solid A-arm in there and a knuckle in there. And again, all of these things are still being constrained to that base geometry at first when you're creating the models. Later on, you're going to have to constrain them to each other so they'll actually move properly and you can see how everything interacts. But when you're first starting out, you want to make sure everything fits that skeleton geometry so that you actually get the desired suspension parameters instead of guessing at it. So I'm going to keep showing these. Now there's a lower A-arm, so you can see how this stuff all fits together. Now there's significantly more involved in the model, but again, all of it's just related to that skeleton geometry. And I'm going to go ahead and show that all of that stuff moves together. I've already got this model constrained to where it moves like that. So if I click on the assembly constraints button up here, grab a piece of the model, you can see how it all moves up and down. But if I take it back to the starting position, you can see that it all fits up with the skeleton geometry. The upper and lower A-arms match the planes that they're supposed to be in, the knuckle and the axle and the wheel. Everything is in the right place where it needs to be. I'm just going to go ahead and show the rest of those. So that was a brief overview. It looks kind of quick, maybe it seems easy from what I did right here, but there's a lot of work involved in actually fitting all these parts together and constraining them and making sure that the geometry is actually what you want. But in the end, you can constrain it all together, everything will move together like you want it.